北川景子さん。こんなとこに中山美穂さんがいるじゃない。北園一郎、僕ですね。この次はなんか多いな。
So we're in this explosion of commercialization, and you're talking about the NASA budget. I'm wondering what the role of the NASA is in the future. Does it will it fold in the military? Will it,
はい、どうぞ。はい、どうぞ。はい。好き？どうぞ。
おもちゃ好きにして。
はい、好き？
おもちゃ好きで。
200 250. はい。はい。はい。200. はい。あとこれ、はい、おもちゃ。
これ200円。
200円。はい。あとこれも使ってっていいですよ。
これ大人使えます？いい
ですよ。それも使っても。
大人使えます？
大人は使えない。子供で、はい。大人は普通ののでありますので。はい。
どうも。
For 2 decades, well, it's back on again, and they're experimenting with new propulsion technology. So NASA is able to do things that don't have a commercial payoff in the near term, because these other companies do need to satisfy their investors. They do need to turn a buck at some point. So NASA will always be doing the things that don't need to turn a buck, that are more pure research, that are more exploration, that are more astronomy. And so for that reason, I'm very confident NASA won't go away. Yeah. Thank you for a great talk. For Dr. Stenner, because Cirque du Soleil did go out in a space
1
station.
本過ぎです。
Last year, just as earlier. So I was wondering about Arctic gravity because when there's no research because all they give to us to buy the spaceship and 2 miles of cable between them, spin it around. It'd be pretty cheap for what size spaceships they have now. Why is more research being done on that? So there are space station concepts with artificial gravity as part of the concept, and in fact that is certainly needed. The longevity record in zero gravity is 826 days for a Russian cosmonaut, and all the people who have been out for more than a year have had serious health problems. So I think we recognize humans need artificial gravity. Mars level gravity 40%, 36% gravity is not likely to be a serious problem. The radiation is more of the issue, protection against radiation. But you're right, the gravity will have to be generated because humans cannot really function in a multi-generational way without some sense of gravity. It's just how we're built. We're built, obviously, with tens of thousands of years of evolution to have vascular systems that depend on gravity operating. Yeah.
So I have a question about, would asteroid mining really be that practical? Because the problem is, you're saying you'd bring it into the Earth's orbit and mine it there, right? But if you made one slight misstep, you could drop it on the planet.
Yeah, that's a good point. People doing this are rocket scientists, so we hope they don't get it right, wrong. But so
I'm saying it's one slip up and you blow up a city.
It may be worse than a city because a 500-meter asteroid is going to take out a small country. Let's say Belgium. I don't have anything against Belgium, but something like the size of Belgium or Iowa. I don't have anything against Iowa either. But you're right. So the asteroid mining thing, let me just flesh it out a little bit more. The technology does exist to steer an asteroid that is otherwise in an Earth-crossing orbit into a captured Earth moon orbit. That's not actually close. That's not like a low Earth orbit. That's not like a few hundred miles above us. That's tens of thousands of miles and highly elliptical. So, but at that point, it's captured. You would then gradually circularize. So that's not really coming close to the Earth. That's not a near miss or anything. Then with using drags like drag from the upper atmosphere and rockets again, you would gradually circularize that orbit, and that would take a couple of years. And again, there's nothing dramatic going on, so you're not risking it just plowing into the Earth because you're just taking the orbit and adjusting it incrementally and very slowly. And then when you circularize it, it'll still be higher in orbit. It'll be much higher than the shuttle is or the space station. If they're a few hundred miles, we'll be talking about 1,000 miles. Then of course you use the space elevator. Then by that time you will have.
Yes, yes.
Yes, yes. This one. Over there.
Oh. Hi.
Yeah.
Cheese.
Again. Again.
Ah.
Ah.
Movie. Movie.
Uh-huh. Oh, yeah, it's okay. Nice. Yeah, thank you so much.
Can I video your video?
Uh-huh.
This
Oh, with this one. Yeah, it's okay.
video.
You want to video?
Oh.
Just press.
Oh,
So what I supposed to do?
Yeah. Start
Hello.
it.
Oh, we are in.
Hi.
Sekarang kita ada di Niigata. Apa?
Niigata, iya.
Kochi.
Echiga
Yuzawa.
Echiga Yuzawa.
Ah,
Dan bersama
Sponsori.
salju.
Indonesia.
Hi.
Thank you so much.
Thank you.
Thank you.
Making replicas. Yeah, it's maybe only 30 years away. Now, printing a human, and biological organism, I'm going to put a lot longer time scale on that because the mechanics of that are extremely difficult. But yes, we could start propagating beyond the solar system and break through star shuttle because it's going to prototype some of the technologies that would be required to do the travel part, if not the replication part. Thank you. Let's thank Dr. Hinkley.
Uy.
Good evening, everyone. My name is Andrew Fracknoy. I'm the chair of the astronomy department here at Foothill College in Los Altos, and it's a pleasure for me to welcome everyone here in the crowded Smithwick Auditorium and everyone watching us on the web to this lecture in the 17th annual Silicon Valley Astronomy Lectures. These programs are co-sponsored by the Foothill College Astronomy Department, by the SETI Institute, the Astronomical Society of the Pacific, and NASA's Ames Research Center, and we're very grateful for their support. This evening's program, we usually have superb speakers talking about sexy topics in astronomy, but we're especially fortunate tonight to have Dr. Andrea Getz, who is professor of physics and astronomy, and who holds an endowed chair in astrophysics at UCLA, and is one of the world's leading experts in observational astrophysics. She heads UCLA's Galactic Center Group. She has received numerous honors and awards, including the Crafoord Prize in Astronomy from the Royal Swedish Academy of Science, which is sort of our version of the Nobel Prize, a Becquerian Medal from the Royal Society of London, a MacArthur Fellowship, election to the National Academy of Sciences, to the American Academy of Sciences, and to the American Philosophical Society. She's very involved with the giant telescopes that are bringing us news from the universe, the Keck telescopes, and the still planned 30-meter telescope. But we're especially fortunate as listeners because she's very committed to the communication of science to the public and to inspiring young girls into science. Many of us have seen her wonderful talks and TED Talks all over the web. So we were able to lure her from Southern California with a little help from our gracious donor who's now allowing us to have people travel for these lectures, which we're delighted to have. And so it is for me both a personal pleasure and a professional privilege to introduce to you Dr. Andrea Ghez.
Thank you. It's a pleasure to be here this evening and speaking at Foothill College and part of this wonderful series. I thought I would start off sharing with you how I enjoy starting off a class at UCLA. I usually ask the students to share with me something interesting about themselves and what they like about UCLA. And I get to learn all sorts of interesting things. But then I share with them why I came to UCLA. And it's this telescope. This is the largest telescope in the world. And it's co-owned by the University of California. Now, with these large telescopes, you have the incredible opportunity to answer some of the biggest questions that we can ask about our universe. We can ask about the origin of the universe. We can ask about the potential for life elsewhere in the universe. And we can also ask about black holes, which is my particular passion in life. So I'm going to start this lecture with a question, which is how do you observe something you can't see? Because this is an essential question if you want to find and study black holes. Because these objects have such strong gravity that nothing can escape them, not even light, so we can't see them directly. So the story that I'd like to tell you today is how we've been able to find a supermassive black hole at the center of our galaxy. And this has not only provided us with the best evidence today for the existence of these truly exotic objects, but it also provides us with a wonderful opportunity to study the fundamental physics of black holes. In other words, how they warp space-time, and also to understand what role these black holes play in the formation and evolution of galaxies. Now, on our journey to the center of the galaxy, we've to prove that black holes exist, we first have to agree on what a black hole is. So while black holes require relatively exotic physics to describe them properly, the way I would like you to think of a black hole today is an object whose mass is confined to zero volume. So despite the fact that I'm going to talk about things that are supermassive, and I'll get to what that means in a moment, they have no finite size. What this actually represents, well, actually, if you think about density, which is just mass divided by volume, since the volume is zero, this quantity goes to infinity. And in physics, anytime you have a quantity going to infinity, it's known as a singularity, or it's a big red arrow saying you do not have your description of the physical world quite right here. Another way of thinking about this is black holes represent the fact that we do not know how to make two areas of physics work together. So we do not know how to make the study of gravity, which is what Einstein's so famous for with his theory of general relativity, so the study of things of lots of gravity. We do not know how to make this work with the study of quantum mechanics, which is the description of things that are very small. And black holes embrace these two things, so we actually don't know what a black hole is. We simply don't have the tools to describe it. But fortunately for me, there is a size that we can talk about that's associated with a black hole. So just keep in mind that physically it has no finite size. But there is an abstract size that we can associate with black holes. This is known as the Schwarzschild radius, or popularized by Star Trek as the event horizon. Alright, so it's the last point that light can escape this object. So in other words, information cannot be communicated from the inside of this to escape this object at this rate. So you can't escape once you get inside. Alright, now, it is also true that every object in the universe has a Schwarzschild radius associated with it. And what that means is that if I can figure out, or if one can figure out, how to shrink that object down to its Schwarzschild radius, then at that point, it would be forced to become the infinitesimally small object known as a black hole. Because at that point, gravity overcomes all other known forces. Those would have to collapse. So you have a Schwarzschild radius associated with you. Your cell phone does, your neighbor does, anything you'd like to turn into a black hole. And it turns out it's relatively simple to calculate. It only depends on mass. So to give you an example, if we can take the Earth and squeeze it down to the size of a sugar cube,
ナスタは
the bigger the mass, the bigger the Schwarzschild radius. So if I were to take the sun and squeeze it down to the scale of UCLA, actually Foothill College, but down to a campus size, it would become a black hole. So not only does this define what a black hole is, but it actually gives you the structure